Okay, thank you for the introduction, and thank you all of you for being here. My name is Erik Calvo-García, and I'm going to present a current project that we are working at in the Materials Engineering, Applied Mechanics and Construction Department of University of Vigo, which deals with an experimental analysis of high cycle fatigue failure of hot forging tool steels. So in order to understand the motivation of this project, I'm going to talk about what hot forging tool steels are, which, as their name suggests, they are used for hot forging applications. They are widely used by many industries in manufacturing of pressure die casting tools and extrusion tools, which are components which are subjected to high thermal and mechanical cyclic loading. So it is important that these materials present high mechanical properties and good fatigue behavior. We managed to get those properties through an appropriate heat treatment, but if the heat treatment is not designed correctly, or there's a poor tool design, or the work conditions are aggressive, that could lead to a premature failure of the tools and consequently to more money invested by the companies who work with that. So the purpose of this research is to analyze high cycle fatigue behavior of two hot forging tool steels. We were going to do it at room temperature, and we will do two different analyses. On the one hand, conventional high cycle fatigue loading, and on the other hand, corrosion fatigue tests. So how did we do them? First of all, we tested two materials under the same H13 specification. As you can see, the weight compositions are pretty much the same, but they belong to two different manufacturers. I will refer to them as A and B. And the heat treatment that they were subjected to were meant to reach the same final hardness of 46 in the Rockwell C scale, but as you can see, the tempering temperatures of B steel were a bit higher. We will see how this may affect it. So the fatigue specimens that we used for fatigue testing were extracted from an actual crankshaft die tool. We machined them. Well, first we applied the heat treatment described on the previous slide to the crankshaft die. Then we extracted fatigue specimens from the block. We machined them according to these dimensions, and we polished them in order to avoid surface roughness effects on the results. The high cycle fatigue tests that we performed were axial load control tests with a stress ratio equal to 0 and 10 Hertz of frequency. And we performed these tests until either failure of the specimens or to reach 10 million of cycles. Corrosion fatigue tests were done using the same parameters as described before, but we introduced this handmade setup where we introduce a sponge soaked with a 0.1 molar chloride sodium solution that was placed in contact with the specimen throughout the whole fatigue test. So now the results that we got, first we did some preliminary tests. We took a few samples to X-ray diffraction analysis just to be sure that we were dealing with the same microstructure, which correspond to a martensitic microstructure characteristic for quenched and tempered steels. Then we also measured the hardness just to ensure that we were fulfilling the heat treatment specifications of the specimen hardness, and we can see that not only they were both significantly alike, that we also got the 46 Rockwell C, even though here is a Vickers measurement, but it will correspond to 460 Vickers. And we also performed tensile tests on few specimens, and here we did see that B steel presents not much higher, but I think it was a 7% higher tensile strength than A steel. So here I'm presenting the fatigue results under normal test conditions, let's say. In y-axis we have the maximum stress, and and in the x-axis the cycles to failure, and we can see that these steels are able to reach almost 1,000 of megapascals during 10 million of cycles, which is quite impressive. On the other hand, corrosion fatigue tests are expected were much led to much lower fatigue lives, and this reduction was more accentuated at lower stresses than at higher ones. Then we, through regression analysis, we got like some fitting curves of each material and test condition, which are presented here. And what we got was first, of course, what we observed that for corrosion fatigue, the tests, the slopes are steeper and there's no fatigue limit. Like we can see it on the, also on the exponents of fatigue strength here. If we look at the coefficients of determination of these curves, we can see that data is much more scattered in normal fatigue tests than in corrosion fatigue tests. And what's interesting is that under normal fatigue tests, the Waller diagrams were quite similar, whereas there's a statistical difference between both steels in the corrosion fatigue tests. Actually, the B steel presented kind of, here the logarithmic scale is tricky, but is twice the fatigue life that A steel presented. So we analyzed the microstructures of both steels through SEM images. What we could see was a characteristic martensitic structure with carbides through the images. The first thing that we observed is that B steel presented slightly smaller grain sizes, which is in line with that small difference that we saw at the tensile tests. At higher magnifications, we were able to see more clearly the presence of carbides, mostly at the grain boundaries, and we could see that in A steel presented slightly bigger carbide sizes and more abundant than in B steel. And then we did some fracture analysis where the here I'm comparing like under the same maximum stress both materials. We saw that in most specimens surface crack initiation took place, and also that B steel presented in all tests a much higher crack propagation extension than A steel, which may suggest that they may present higher fracture toughness. And in regards to the corrosion fatigue test, we observe kind of the same features, but here it's clear that the surface crack initiation took place due to the formation of corrosion pits under these tests. And then we also did a fracture analysis through SEM images to have a higher magnification images. We can see that, as I said, like in most specimens, surface crack initiation took place, and we can see it with very clearly in this picture. Then, but in some A steel specimens that failed, especially at high number of cycles, we were able to see the characteristic fisheye region from an internal failure, and in the middle of this circle, like we could see like the presence of inclusions, which might have been formed through. Well, they were formed through the manufacturing process of the steel. So to sum up a little bit these results, what we saw was that, as you already know, probably like crack initiation at high number of cycles dominates fatigue life results. So it makes sense that the presence of the defects and heterogeneities in the steels led to higher data scatter, whereas on corrosion fatigue tests we are kind of inducing crack initiation, and so crack propagation times gain more importance in the results, and thus that's why we think we got less scatter in the results. And just to conclude with the presentation, we saw that this family of steels, hot forging tool steels, present outstanding mechanical properties and pretty good fatigue behavior under normal conditions. Through corrosion fatigue tests especially, but looking at the crack propagation areas, we kind of they suggested that B steel may have presented higher fracture toughness due to probably due to the higher tempering temperatures and the finer microstructure that we saw, because it had smaller carbide sizes. And as future work, we are working currently on developing these tests at higher temperature, so we can kind of replicate the actual behavior of this material during working service, and we would like to also perform some measurements on fracture toughness to ensure if this difference is there. Finally, I would like just to acknowledge, the co-authors of this project, the Spanish Center for Industrial Technological Development for the funding, and the CACTI staff from University of Vigo for their help in sample characterization. And thank you very much for your attention.